structures for wind energy, tidal energy, automotive, architecture, oil and gas structures, pretty much in every field where composites are structural and highly loaded. In this present paper, we will discuss the trace, which is a new theory that Steve Tsai from Stanford University has developed. And we've been working since March together with Steve and his team at the Stanford University. And Composite is one of the only software today who has been using and benchmarking trace against traditional design. Our aim since 5 years is really to make composites more cost effective. So we'll start the presentation with a brief overview of our objectives. We'll discuss briefly about composites, then a very short introduction about composite, the key elements, then an introduction to the trace, and then the trace and composite, and then obviously what's coming next. It's very difficult with, oops, okay, composites. Are they really easy to adopt? And they mix materials, process, and design. And we are in business with Structeam to provide consultancy that there are people who need help. Composite is selling, so people need software solutions. They are inherently complex because of the combination, the interactions between material, process, and design. You create your composite material in the mold. You buy the constituent. So Daniel mentioned is representing a prepreg company. It's one of the parts, but it's not the material in its final form. And that makes it extremely tricky to adopt composites. There are a lot more modes of failures. So in metal, you design with Van Mises. With composites, you've got 30 modes of failure per ply, then you combine them in various directions. It's really good for the engineer, plenty of options to look at, extremely satisfactory, but for people who make decisions, it's cost, it's time, and it's difficult to make a decision. Okay? Well, the engineer, the composite engineer is lucky. He's got a very wide material palette, different fibers, different resin, different cores, different adhesives, and then you put the manufacturing process in the middle. So the number of options that you really want to look at, and maybe the car part manufacturers can confirm that. You know, is it RTM? Is it prepreg that I need to use? Is it thermoplastic, thermoset? In which format I need to buy it, etc. The supply chain is extremely complex. It's difficult. I guess that most of the presentation today were about composites are great. Well, composites are difficult. Hopefully we'll try to bring an answer to that problematic. Manufacturing technology, which one? Wet lamination, press, infusion, pultrusion, prepreg resin film infusion. Do I need to automate? Depends on my volume. What is the cost of that? How mature is the industry? And all those questions for the non-expert are only question mark. Every time you progress further, you'll create more questions. Okay? So consider myself a composite expert, and part of our role is to make it easier. And that's why we put composite there, and this is where we met with Steve Tsai and his theory to make it easier to adopt. If it's easier, it's going to be cheaper. It's going to be faster. So we talked about material processes, testing. All of you have had experience testing before. Did the testing answer your question, or did you have more questions after you tested it because you were not quite sure that the result was what you expected? How much testing did it cost you? Usually much more than you anticipate. So when we do a budget for testing, we usually, let's say it's 5,000 euros, we'll usually provision 10 because there'll always be a problem somewhere. Because you need to trace from material right up to the end. This makes composite really difficult for industrial applications. The growth of the composite market is on the large industrial application. Carbon fiber industry and those applications started for the niche applications, sports car, leisure goods, racing boats, and those, extreme weight saving application. Now we are talking about mass automotive, oil and gas, architecture. It's different beasts, it's different market sectors, it's different requirements and different risks. To manage your risk, you need to manage your materials. You need to control your design. You need to control your processes, which is where the composite industry is going step by step. Okay, material, complicated, processes, complicated, design, doesn't quite look very simple, huh? Any of you are design engineers? Yeah? Familiar with this kind of stack-ups, all every colors, and so it looks too complicated for me, But design should be simple, because from your design, then you'll select your materials, you'll select your manufacturing techniques, okay? Obviously with cost and manufacturing constraints, but design should be made easy. So a short note about what is design. I think we are all young enough not to remember that. Not sure about our professor friend. Maybe he did a little bit of drawing. Sorry? You're one of the... So, well, personally, I don't remember this, and I'm very happy to be living at today rather than 40 years ago. My drafting skills are not so good, and I'm very happy to use a computer. So we are strong believers that basically the technology needs to be at the service of the engineer, and engineers shouldn't really spend time fighting tools. They should use them to spend more time creating and delivering solutions to the industry, which is why your employers pay you, why you're researching, etc. Okay. Today, and that's an element of technology, it's a new reality. Composite is a software company. When you look at traditional engineering software, it's one person, one license, one computer. It's very good, because if the person who is at that computer is on holiday, nobody else can use it. It's a bit extreme, but that's pretty much the model. Today, this map at the back is the largest American data centers for the Amazon cloud, Amazon Web Services. Composite is supported by cloud solution. It's web-based. It's one entry point for all your companies. It's subscription-based to make it easier. That's technology that serves this, and we need the same for the composite industry. It works in IT. We need that in composites. How can we make them simpler? This is a bit of an interesting point about design. Design engineering, is it an art or a science? Maybe we should ask, can I ask you to be a contributor, because you're a professor. So what would be your point of view on this?
If you are on the right side, probably you are richer.
Yeah.
And if you are on the left side, you are happier. I don't know.
It depends. I think most engineers tend to be analysts. It's easy to be an analyst. You have a problem, you check whether it passes or fails, you use a tool, etc. With composites, engineers need to be design engineers. You need to have creativity with material, with the processes to combine all those options. Okay? And that's where it's different from traditional materials. So we tend to lean towards the idea that design engineering is an art with a bit of science support. Okay? So as soon as you work in composite, and I think that's one of the very rewarding things for me after 15 years in this industry, is that it's never the same problem. Yes, there are problems or challenges. Let's call it challenges. Problems is a bit negative. And our brains are linked with that. The left brain is logical, sequential, rational, analytical, so that's the analyst part. The right brain random, intuitive, holistic, synthesizing, subjective, and look at things on the whole. Okay, so that's more the design side. And with composites, whether you want it or not, you need to mix both. That's the same for the manufacturing engineers, not just the design engineers, because you need always to find new solutions. So this is why we put Composite as an integrated suite of web-based solutions to develop your composite project. Okay. Solution architecture has several layers. Web-based, so for the users, as many users as you want with one subscription. Geographical location do not really matter. Software deployment is easier. Each of the customers are updated at the same point. Those of you who use CATIA are very happy every time they receive the 10 CDs, and each and single machine needs to, each engineer needs to update his own CATIA from version 22 to version 23. How much does it cost to an organization? It's just tremendous. And is it what engineers want to do, spend time updating softwares? Security, well, this is one of the things where the cloud, every time you say cloud, you say, ooh, security. Maybe the fact that many celebrity iPhone pictures leaked onto the public domain is not so good, but there are strategies for that, there are certifications for that, and that's the solutions we use. And scalable. Maybe today in your team, you've got 5 design engineers using composites. If you're successful in your early development, tomorrow you'll be 20. You don't want to pay 4 times more to grow for that. You want to be more efficient. You want to scale, to have scalable solutions. With Composite, you get a centralized solution for all your project and user roles, material data for all your company, management of your engineering process for your bill of materials, engineering and manufacturing bill of materials. Can be used to some extent for your knowledge base about composites, and you can standardize your reporting and bill of material reporting. So you make those tasks that are, it's not nice to write a bill of material. It takes time, you spend time in Excel, in Word, and it's not really rewarding for an engineer. You'd rather develop solutions. And then productivity in your composite product development, project management, design and simulation, and quality. We see Composite as a complementary solution to existing software infrastructure. We don't intend to replace ANSYS, Abacus. We don't have 6,000 developers with us and 20 years of experience. But we see that we can optimize the use of solutions like Abacus and ANSYS. Instead of having an engineer full-time on this, you can cut that down to 20% of his time by iterating within Composite and then validating with those heavy-duty tools that are industry certified. It's all about saving costs and time. From the feedback we get from our customers, we get 40% faster application development by the fact that it's web-based, composite-focused, and that you don't have limits on users. Key elements, accessibility, focus on design, on that creativity side. You know, it's not that you don't have any limits, but if you want to test something, it will take you a few minutes rather than a few days of work. Okay, and efficiency. Okay, let's get to the technical bit. Don't ask me too technical questions. I'll try to do the best I can. Okay. What is trace? Trace is a news theory that was developed by Professor Tsai and Daniel Mello from Stanford University. Here you can see what, well, most engineers, including me, try to avoid is to go and deal with the invariant stiffnesses. Okay, I don't really want to deal with matrices. Okay, and that softwares do that for me, Composite or another one. What is quite amazing about the trace is that Daniel and Steve, in all their research, they managed to see that with different laminates, with different configuration, whether it was single skin sandwich, they identified that the trace, so the sum of these 3 matrices term, there was a constant. There was an invariant directly related to the Young modulus, the longitudinal modulus of the product. So they managed to convert this matrix with 9 terms into one equation. It's a pretty radical approach. Because if you look at it, if you convert 9 terms into one, it looks like metallic design. You're back to von Mises to some extent. And if you're back to von Mises, then what does that mean? So think about material qualification. If you've got one property, that's a relief. The test house will probably lose a little bit of business, but you'll gain time, you'll have less questions, you'll get faster to your answer. Okay? So the trace and the relation with the Young's modulus of the material is absolutely key. So following this theory, there is a question of scalability. What do we do from there? Okay, that's the theory. Now in practice, and this is where composite comes in play, what did we do? We discussed with Steve, agreed a milestone plan, and we started by looking at laminates. Does it work on laminate? Classical laminate theory evaluation. And we compare traditional method with a trace-based approach. Okay? So trace is an invariant property like the Young modulus. Trace is invariant, is a material property like the Young modulus. Okay? So we introduce a new material property, but one. Look at your characterization of a carbon unidirectional. You'll have about 25 properties at the minimum. There we have one. The trace is an invariant, and it's a powerful scaling factor and design tool. Okay? So here we've got, the trace and the specific trace. This scaling was done initially by Steve Tsai and his team on laminates, at the laminate level only. And when we kicked off our joint project together, we looked at beams, sandwich panels, because that's what the industry is using. Okay? And we wanted to see the relevance with this design, with a real design case, before going too far and implementing it into composite. One of the key elements of trace is in the laminate design is the homogeneization. Use thinner layers, but use more of it. Okay, that's one of the principles that Steve has been preaching for many years. And this is, if you increase the degrees of homogenization, you get fewer angles, thinner plies, and you get a behavior of the material that will be closer to isotropic materials or metallic materials, which is what those industries where the future of carbon fiber composites is. Okay, those industrial sectors. I'm not too sure I understand that slide. It looks very complicated. Okay, but basically, what has been done is that there are many stacking permutations that have been checked to assess whether the trace was affected by the fiber orientation and the stacking sequence. Okay, and that was the early work that Steve Tsai did and confirmed that it worked. Okay, this is an example of an application of the homogenization. Is that by having extremely thin ply and an asymmetric panel, you end up with no warpage, okay? Which can be interesting for the automotive application because, as soon as it warps, you've got a bit of a quality problem, And I'm sure you want to push asymmetric laminates as much as you want, or to have the freedom to do whatever you want. Another application of the homogenization and the thin ply is just about the failure. And you see that with the thin ply, it's much more contained. It behaves much more as an isotropic material. it feels really strange for me to talk about composites as an isotropic material when, for the last 15 years that has been exactly the opposite. But you will see where I get to. Well, here we've got our traditional testing pyramid. We start with the coupons. How many coupons do we need for an aerospace qualification? Maybe Daniel is one of the ones that is well placed, but it's far too many. Then elements, then details. With trace, you need one and one only universal Ply data for each carbon fiber product that you're going to use. Okay? So it's only a fraction of the cost. And it's actually one that is easy to test. The Young modulus is pretty straightforward. What we've done with Composite is to evaluate the trace and validate it with Composite on a panel design element. Okay? To see the scalability. What is the applicability of the trace-based design on real structures? Because at the end of the day, all these theories are good if they are used in the industry eventually. Okay, it won't happen tomorrow, maybe even if I'm really convincing, but it needs to be useful for the industry. Otherwise, there is not so much benefits. So here we can see a comparison of the trace-based results versus the FEA-based results computed by using with Composite. On the top row, it's different combinations of laminates. So there are single skin panels, there are sandwich panels with different stacking sequence, different homogenization rules. You've got the NCF layup that gives you an indication of the different fiber angles that were used, what material based were used. We use different moduli of fiber to see the scalability as well, from standard modulus to intermediate modulus. Okay? We've tested different NCF architecture between thin and thick plies, etc., to see, does it apply to everything? Does your laminate need to be homogenized, etc.? To really answer those questions, to be able to say, okay, are we confident to look for an industrial pilot customer to implement that on a real design or to re-engineer using the trace-based theory an existing design and see whether it's applicable and that will deliver the savings that are expected. Okay? The weight factor is the discrepancy between the trace and the FEA. On the next slide, you will see it a little bit more graphically. But you can see that it doesn't exceed 5%. Okay? How much uncertainty do you have in your loadings? 5, 10? In the loads that you apply on the structures that you're calculating? More than 5% for sure. Okay? So this, if your analysis is within 5% using a series that saves you a lot of time, you might as well add that onto your partial factor. It's not going to affect you that much. Okay, and then it's still early days. It needs to be consolidated, developed further, and we are really at a point, is it what the industry needs? Okay, so we have a very good correlation. One of the points is that we compared against an aluminium design. Steve comes from the aerospace industry. His institutional partners are Boeing, Bombardier, and for them it's all about going from aluminium to composite. The same in the car industry, I suppose, to some extent. The weight reduction compared to aluminium is slightly overestimated by the trace by up to 3.5%. For an engineer, that's a lot, 3.5%, because it's not 0 or 0.1%. For somebody who is making commercial decisions and so, that's acceptable. Okay, so this initial step was very successful in showing that trace can, within a number of parameters, materials, layup, and ply architecture, deliver consistent results, okay, which gives confidence to bring this to the next step. Here you've got, on a graphical form, the comparisons that were done on those panels under a variety of loadings, so some were in bendings, they were in plane loadings, etc., to really address the typical design case that a composite structure will be subject to. And you can see that the consistency between the two results are quite high. On the left-hand side, you see the weight factor between the composite solution, which is on the graph, and the aluminum solution. And the comparison between a traditional method, with all the qualifications that it implies, all the analysis that it implies, and then the trace. Okay. So this phase was.
Sorry for interrupting you, because I'm a bit confused because you were at the beginning referring to convenience criteria. So are those data referring to thicknesses or to strength?
Stiffnesses.
Okay. Because this side is quite well known for failure criteria, but it has nothing to do with failure.
This is with stiffnesses.
Okay.
Yeah. Sorry. No, that's a good question. It's part. The stiffness and the strengths are, some structures are.
Quite distant.
Yeah, stiffness critical or strength critical. For the strength, this is still being assessed. Okay. I think it's quite obvious that it's stiffness. We didn't mention any failure criteria. Okay. So what does it mean is that within a few weeks from kicking off the project, we were able with Composite to analyze and to beautiful. Sorry. Within a few weeks of starting the project, we were able with Composite, which is a new product, to evaluate this new theory and to come up with some next steps and some validation point that enable this theory, hopefully, to move to the next step. Okay. So this was helped by web-based agile design software, where we shared, obviously, our across the team members, the access, and everybody could work together. What does this mean from a composite product development? This is traditional traditional methods with design, analysis, and material qualification. And with a trace, you can with incremental development, optimizing your various processes, understanding more within composites within your industry. You can lower this over time, but you still will have a cost and a level of pain that will be relatively high to develop your composite application. Using Composite, we help. Using Composite and the trace, then this can help further. Okay. At the end of the day, everybody is clear, and that's why I started this presentation not by saying composites are great. Composites are difficult. Otherwise, why would we be working with it? Why there will be technical people all over this show, all with their own little solutions. There are different ways to skin a cat in the composite industry. But I think there are means to make it easier. Okay. Obviously, great fusion between the two. Hopefully, we are trying to do that well. So what's next? You may have seen that we've done a number of press releases jointly with Steve Tsai over the last few months. We've established contact with a number of parties that are interested to test and trial this new theory and benchmark this new theory on industrial applications. So We've had interest from Airbus, from Bombardier, from landing gear manufacturers, and a couple of other parties, and we are actively looking to get an industrial partner to apply this and demonstrate that in a practical case, this delivers the benefits that are expected. Okay? So trace looks very promising as an alternative to current composite design practice. Making composite easier, I think, is everybody's, challenge at the moment. We are actively developing and implementing trace within our platform ahead of the next steps. And obviously, as I mentioned, we are seeking industrial partners, product manufacturers, OEMs, and material manufacturers to further extend the reach of trace within composite and the composite market. Okay.